me now, you're talking at the level if you're going to be going in a programmable controller, right? You're using that's the logic then. Is there an
Well,
and an or?
that's a basic Boolean algebraic functions, but it can help you in hardwired circuits also, because just as we described here, the three devices all.
So let's
had
try
to be
this.
on.
I'm going to try to work toward it. Okay, this motor should run if the switch is closed and if the overloads are not open and if the float switch has risen to a level that closes the contact. Then you would have voltage to the motor. Let's put it that way. Not that the motor's running, but then you'd have voltage to the motor.
Yes.
And Eric, you said that we could put a flow switch in this motor, right? And with a flow switch, we could then determine whether or not the motor is actually pumping any fluids.
Right.
And if the switch is closed and the overloads remain closed, and if the contacts for the flow switch are closed, then the motor should be running. Then we need to make sure we have liquids. And if we don't have liquids, then we can have something else to say through some other computer control or something like that, saying, well, then turn off the motor. If we wanted to protect the motor against, let's say, a lack of movement.
Or we could use the normally closed contact and turn on a pilot light.
Oh,
or an
you're
alarm
saying,
at that point.
You're saying I could add a flow switch here with a normally open contact that if it flows, then the green light come on. We could,
Yeah.
And if it doesn't flow, well, then the normally closed contact would be closed, then the red light would be on. So I
Yes.
could tell whether or not there's any liquid moving just simply because I can see the lights on. And the red light would be on as long as that normally closed contact that's in the flow switch here. But the green light can only come on if the green light bulb is good, and if we're having flow, and if we have voltage, and what have. Then we can even put another light saying, do we have voltage? Right? You can have a light that just says white. Okay, is there even any power for this signaling circuit? Okay, we got white. Well, then if we have white, then we might have a red condition or a green condition. So you can see this thing can build up. What do you want to know? How much money do you want to spend? How important is it to you to know this device? Or take that information. Well, if green comes on, then we want this condition. If red comes on, then we want that condition. So we're building. All right, control device with multiple contacts. Most switching devices come with at least 2 sets of contacts. Here's a float switch. A float switch with normally closed sets of contacts, normally open, which means we could use it in that same circuit. If you close a switch and the contacts are closed, which means there's no liquid in there, then if you close the switch, the motor runs and it fills in this, let's say this tank, and once it fills it sufficient, then it would rise this lever and it would then open the contact and stop it. Dan, show us that device that would do that, where as it rose, it would then open a contact.
That would be in this configuration when the
So the contacts are closed, and then
contacts are closed, and as the liquid level would rise, then you would open your contact.
Got it. Now, we could take the same device, because it comes with normally closed and normally open contacts, flip it the other direction, that if I close this switch, well, then the motor's not going to run. But if liquids happen to can enter to some point, then we would stop it, or rather, we would close the contact, and then we'd activate the motor. So show us that one. So the liquid, the contacts are open.
That would be an example of pumping out of a vessel or a container.
No.
Or if you had water, it would pump until it's too low. Or, as you were alluding to.
Okay, right now that's open, right?
Yes.
So, but if liquids rose,
So if liquid rises,
it then is going to activate close the contact, and it's going to do whatever we choose it to
Yes.
react. In this
Yes.
case, it's going to be closing, we're showing pilot circuitry, but we're showing really line power going here.
Yes.
So we'll probably have to make sure these wires are full-size conductors. All right, that's good now. I think the point is contacts come normally closed and normally open. There's a point that I see, I won't say I'm getting confused on, but I can see you have to be aware of, that sometimes you're making and breaking your power conductors, because we're having power. And sometimes, which we haven't really got to too much yet, you're making a braking control. Right now, we're just talking about logic. We're talking about making braking contacts. And so far, we've been talking about power switching, not control circuits, even though you're showing some kind of control devices. All right, that takes care of Unit 4. Now we're into Unit 5, magnetic control. That was all like manual control. Now we're going to get into some real controls. This unit introduces the concept of magnetic remote control devices used with both motors and other types of loads, such as lighting. Electromagnetic control. When installed as a component in a motor starter, the energized coil magnetically pulls in a plunger with movable contacts that make contact with matching contacts from the power circuit or the supply circuit. My assumption is that you've taken an electrical theory course, you understand how currents travel, you understand electromagnetic fields, and you understand a coil that it's going to draw in an armature or it's going to push an armature out depending upon the configuration. So let's take a look at this graphic. All right, we have line 1 coming in, and then we have T1 going out to the load. That's, I don't know why T, I don't even know why line, but it's what we call it. And then we have a contact, and it's open. So right now, it's a contact that's open, and then we have some kind of control wires that would be connecting right here. We probably should identify this as the control conductors right here. So we have control wire. Let's say this was a 24-volt coil. If this were a 24-volt coil and we applied 24 volts to the coil, then we would energize this coil. It would create a magnetic field, and in this case here, that armature, which is what moves back and forth, the armature would be pushed in, and that would then close the contacts between line 1, making power continue on to terminal 1. Now that's just showing one contact. So here's line 1. Let's go back here. That's your line 1. It's nice and black, so it comes in. Internally, it's open, and then we go to terminal loads, and that would be T1. If we energize this coil, it then closes those contacts internally, and we have power. Let's take a look at it in this picture. That's the 3-phase contactor right there. Here's, let's say, your coil terminals, which would be your control wires. Let's say we're 24-volt control, or 120 or 480, whatever you want it to be, 277. That if you energize this coil, it will take this armature magnetically, and it will push it, this device, or push in this direction. When it does that, line 1 connects to terminal 2. Line 1 now goes to terminal 1, rather, I'm sorry. Line 2 makes contact to terminal 2. So then line 2, contact goes to terminal 2. Line 3 will come across there to terminal 3. Line 3 goes to terminal 3. Anything you guys have here special that you want to say? So that's how a magnetic contactor works. You know, one of the words that, I'll say it now and I want to say it again a little bit. One of the words that always bothered me is like when you call it a contactor and you call it a starter. Steve.
I was just going to say on this type of frame that you have on the screen here, they want to be careful what position you mount it in, because if you mounted it upside down on some of them, they wouldn't open. It has to require the springs to come open and so on. So the mounting position is important.
So you're saying I might take a contactor and not be aware of this, and I mount it, let's say, on top of something, and the gravity might close those contacts.
Yes.
Steve, what do you got there, Dennis?
Well, it's the contactor, you know, and basically what we're saying, what I think Steve's saying is holding it like this instead of mounting it something like this.
Yeah, you got to look at what position you're putting it in, because some of them require spring or gravity to open.
Right.
Is there a button that you can push those contacts in? I mean, can you push the contacts in? Can you push something on there that the contacts will?
Reset.
I believe it's
Usually.
underneath from the bottom now. That other one would.
Yeah, sometimes they're on the side.
Okay, so can you see that there? Huh?
Yeah, this one here.
Okay,
is
show
on the
us.
side.
That would be what? That would be closing the
Right now,
contacts?
right now, this one here and this is exactly what Steve's talking about, is to where this one here sucks it up to where now it actually reads on, and that's off. So if you put this in the upside down position like this, now it's being forced open all the time, and to close it, it's got to push it away, which it's not going to close.
Steve,
And
do you
so-
have something you show us a cutout that you
Yeah,
can
if
show?
we could get a real good zoom on this. Get my finger in the right place here so I can show you. This raises up when it's energized, and then it depends on gravity when you de-energize it to drop back down.
Ah.
If you can see that cutout
So
of
there's
that.
no spring there. It's just using gravity to drop it out.
Right, this is just using gravity.
It's the same way with
So
this
if you turn it, okay, and flip it
So
around the
if
other
I
way, what
mounted
happens?
if I mounted it upside down somewhere,
It's already closed.
one. Exactly.
and it's probably not going to be as solidly closed as it should be, so it's actually going to be arcing, and you're going to really burn it up.
Got it. Okay.
And then you started to bring up another comment, Mike, about difference between contactors, starters, relays.
Yeah.
Of course, the difference between a contactor and a starter is this overload block here. If it didn't have this overload block, it's just a contactor. And the difference between a relay and a contactor has to do with the amperage, and that might vary with manufacturer, but usually about 30 amps it becomes a contactor instead of a relay.
Okay.
Also, with multiple poles, your relay, you can have several poles, like 3 or 4 poles, but if you have something where you're switching like 12 poles, then it's going to be a contactor, not a relay.
All right. The principle's the
It's a
same.
manufacturer.
The principle's the same.
Yeah, principle's the same, it's just a sizing situation.
Power sources for the coil and the control circuit. There are 3 basic ways to provide power to a control circuit. All right, let's take a look at this. One, all right, here's the control circuit. You see the smaller lines, which is exactly what we're looking for. Now we're starting to get into control circuits. Here's our symbols. Normally open contacts, overloads shown normally closed. This, we haven't talked about that, but that's going to be an overload device. That's your motor. Here's your T1, T2, T3, your terminals to your motors. Line 1, 2, 3 coming in. Okay, so if I close these 3 main contacts, this motor will run. I got it. I come off of terminal 2 with a terminal. I go over through overloads in series with the overloads, and I bring power over from terminal 2 over to the motor. Now, in reality, voltage is actually traveling, to the coil. Voltage actually is traveling through the coil over to this one point right here. So really this is one phase voltage and this, right? So right between this point and this point right here, I should measure how many volts. If this, 240, right?
240.
So that's another way for troubleshooting. So I have 120 coming in here. I have 120 going through the overloads, which are closed, to this coil, continuing on, but I'm not shading that. We don't need that to that point right there. So in reality, that would be 240 at one point. All right. Let's see what else we got here. Okay, we got the 240 on the line. Oh, the question was, how do you get power? Well, we're just tapping right off of the line of the branch circuit conductor supplying that particular starter. Because it had, Steve, you mentioned already, so I'm going to talk about it. Since there was overloads in that contactor, then we call this a starter. I don't know if that's an industry standard or if that's just something. Dennis, what you got there?
Well, and I was just going to mention that a lot of times you're going to see that your manufacturer is going to have a lot of the material that you're covering or the wires that you're talking about there already pre-wired. And so you're coming off of your contactor, you're coming down, and you actually go down to your overload contact down here.
All right, let me show you what I got here on the screen, and then you show me physically where it goes. You ready for this? And we do one step at a time. This is T2, right here. Show me where that T2 is on your...
Right here.
Isn't it? Is it right there? Is it? Can you see the wire connecting to it?
Not on this one. This one just comes off of the coil itself right here.
I gotcha.
It has a screw on top where you could replace
Yeah.
put a wire.
Okay, so it would come off of right there, right?
Yeah.
Yes.
And then it goes over to the coil,
Here.
right there. And that's your coil, terminal. And then the other wire that goes over to the start button or goes over to terminal 3.
Terminal 3.
Is it marked terminal 3, by the way?
Well, this one here is
Right there.
right here's 3. So
I see
here's
what you're
your
saying. I see. It's only having the... Okay, I got you, what you have there.
right.
All right, so the point is I'm trying to make here is how do you get power for this control circuit? We're coming off of the branch circuit supplying that actual motor. And there's a lot of rules associated with that, but right now that's how we get a source. Another way to do it is to go ahead and come off of the branch circuit conductor supplying that motor. Let's follow. Here's a disconnect. Okay, it's just a knife switch, isn't it? It's not fusible. So we close it, power comes over, so the M contacts are open, but if they were closed, then power goes through the overloads, to the terminals, to the motor. Okay, that's fine. That's irrelevant. How do I get the control circuit power? Well, come off of line 1, come off of line 2, and supply a transformer on the primary, which would then give me secondary voltage. In this case here, go from 480 down to 120. And we mentioned one of the advantages of control wiring is that you can operate with lower voltages. And here would be an example. Do we have any of these? Well, we have one that has a transformer in it, but we'll show that later on. We're not going to show it now. So that's another way. Tap off the branch circuit and then step the voltage down. That's number 2. Number 3, well, you know what? Just go to a breaker somewhere. This case here, pick up 120 volts. And the branch circuit wiring going to the motor is unrelated to the branch circuit that's used for the control conductor. That's the third way you can get power. Let's talk about the coil application. All right. We have a coil. Again, we keep saying motor control, and really it should be control and signaling. Let's see what we got here. We got line 1. We're going to this push button, I don't know if you can see it or not, but this push button is normally open, momentary close. Here it is right here. Normally open, push button, momentary close. So we go open. Let's follow here. Line 1 to the open button, to the solenoid, to the neutral. Right now, the solenoid is not energized. If I push button, this normally open push button, if I push it, then I will energize the solenoid. So if I press this button, I close the contact, I energize the solenoid, and if I energize the solenoid, it's going to draw in this armature, and this lock, a dentist's office, you go to a bank, and so they press a button, it energizes the coil, it draws in the armature and unlocks the door. Now that's called failed secure remote solenoid. And what that means is that pushing the normally open push button energizes the solenoid door lock. By pulling the plunger in, the door can be opened. Releasing the push button de-energizes the solenoid, allowing the plunger bolt to return to the lock position. And what it means by failed secure is that if you lose power, then that door is locked and you're not coming in at all. So you can see where a prison would probably be a good idea to make sure that if we lose power, then all the locks are locked. But then again, we might have next. Now this is going to be fail safe. The other one was what? Fail secure. So in a fail safe condition, let's see, we have line 1. This is normally, let's go here. Line 1, normally closed, solenoid. That means the solenoid is always energized as long as the push button is not touched because it's normally closed. That means that here is the door lock, and if it's pushed, then it will be locked as long as the push button is not pressed. So this one, if you press the button, then it will de-energize the coil, and it will then have this armature go the other direction because the lock is on this side here. Then it would unlock the door. So if I go to a doctor's office or I'm in any kind of facility and the doors are locked, let's say a bank, the doors are all locked, the whole facility. So if somebody comes in or a pawn shop, I say, I think I'll let that guy in. You press a button. Well, the solenoid was energized. If you press a button, you de-energize it. Now the armature draws back, unlocks the door. And then, of course, you release the button, it locks it again. But if you lose power, you want to make sure that people can get out of the building. So if you lose power, guess what happens? As we show here, it's fail safe. If you lose power, then the solenoid retracts and the doors are unlocked. Eric?
This is one reason, because of the complexity of this system, that what's very common nowadays is just simply to use magnets. And you'll see the magnets on top of the door frame, and the magnets will hold the door closed. And so it's an inherently fail-safe system.
So what you're saying is that you're using a magnetic field. It's a solenoid, but except it's going to be drawing it, it's holding it closed.
Actually, yeah, it's just a magnet, and the door frame is metal, ferrous. And so the magnet just holds the door closed.
Got it. Contactors. Contactors are relay type switches used to open and close power circuits. They can be manually or magnetically controlled. So here's a manual contactor, line 1, line 2, line 3, T1, T2, T3. This is basically a toggle switch, isn't it? You press the start button, you're closing the 3 main contacts. There's no magnetic coil. This is just simply a manual switch. And then you press the stop button, which then manually opens the 3 contacts, and then the motor or whatever the load is stops. Over here, we're coming off of line 1, line 2, line 3. Oh, here's your line 2 providing power over to one side of the coil. Is that right?
Mm-hmm.
And then here is line 1. I don't know what it's going to be doing back here, whether it's coming back through here, going to line 2, but it's irrelevant. What matters is that if we get voltage to both terminals of this coil, we will energize the coil. We will then close the main contacts. Line 1, 2, and 3 will then provide power to T1, 2, and 3. Well, let's take a look at this picture here. All right, here is a magnetic contactor, single phase. Line 1 has power to one side of the switch. It's normally open. Line 2 has power to one side of the coil, even though the voltage in reality continues on to this point here. We're only just showing that really the coil has some power to it. If I press the button, then line 1 power goes over to the other side of the coil, and line 2 is at that coil. That coil is energized, and if you energize the M coil, we probably should mark these contacts as M contacts. It would then close those M contacts related to that M coil, and then you have line 1 to T1, line 2 to T2. If we go to a 3-phase, line 1, line 2, line 3, these contacts are open. Going to T1, T2, T3, power goes to the normally open push button. The M coil is not energized, so therefore T1, 2, and 3 is not energized. Press the normally open push button and momentarily close it. Since line 1 is supplying one side of the coil, now that you press the normally open push button, it was line 2 to one side of the coil. Line 1 goes to the other side of the coil. The coil now is energized, and it closes those M contacts. And now T1, T2, and T3 is being supplied by line 1, line 2, and line 3. The load is operating. Let's talk about magnetic contactors. And I think you guys had something where, Dan, do you guys ever push these contacts in to find out what's going on, to measure voltages? Or because if you push these little tabs in, you can actually push the armature. You can make and break the contacts. And we've seen, I think, a couple examples where we're able to move something. Tell me about, in real life, in practice, what goes on?
People can do that. You can push in even like on this contactor. You can manually push those in. It's probably best to have your arc flash suit on when you do that.
Yes.
And with the newer regulations and whatnot, that's becoming less and less of a day-to-day practice.
Eric, what do you got there? Same thing?
Here's one right here. You can't get it with your finger, but you can get something to push this in with.
Mm-hmm.
All right, let's
This has a little.
let's just talk about safety here.
Don't do this at home.
You know, in the 70s, and I worked as an electrician in the early 70s is when I started, we didn't have OSHA. We didn't have safety. And I worked in high-rise buildings, and there were no guardrails. I mean, you just simply You walked off the building if you didn't pay attention to what you're doing, and things fell down and hit you in the head. And there's big change happening in the last 40 years, and now we have to be very careful of an arc blast. And this is not the time to talk about it, but we're going to slowly start bringing in safety applications, and that is what Dan is saying is that if you push that, and Eric showed, well, you can bypass it because you couldn't push it with your finger, so then you kind of get something like a screwdriver, and then you kind of point it in there, that there could be an arc blast. And we're going to talk about that probably at the end of this DVD, if we have time. If not, we're going to get it by the end of the next DVD. But somewhere in there, we're going to talk about practice. And the number one thing is everybody wants to be able to, and you want to be able to have your employees, you want to make sure yourself or whoever is working leave the way you came to work. And if people want you to do things that, we all have done things, if you've worked in a trade, that we can look back now and say, that really wasn't a very good idea. And some people weren't able to survive the things that we got lucky that we got away with. So do not push that in there while the circuit is energized. If you want to lock it out, turn it off, lock it out, de-energize it, tag it, and then say, hey, then it's troubleshooting to find out do you have continuity there, or maybe an ohm meter to find out what's the contact resistance, but you don't want to do that because it can be done. Any other comments you guys want to make at all? All right. All right, but for a fact, that can be pushed, and it's something that we don't want to do. Contactor power contacts. Contactor power contacts. Where there's no power to the coil, the main power contacts are open. When power is applied, the energized coil closes the main contacts, which then energize the terminals to the load. We've kind of talked about that already. Let's see what we got here. We got coming off of line 1 to a normally open switch, going over to this coil. Terminal 2 is already supplying the side of the coil. That's your normally open push button. Line 2 supplies one side of the coil. Line 1 supplies the push button. Line 1 supplies the push button. From the push button, we're going over to the other side of the coil. If you press this button, then you provide voltage to the proper voltage to the solenoid coil. That coil then closes the contacts, which we've talked about earlier, makes line 1, 2, 3 supply T1, 2, 3. We're already kind of ahead of the game on that one there. All right, 2-wire remote control circuit. Here we go. All right, normally open switch. The coil is de-energized. Come off of line 2. Close the switch right here. Well, if you close this is not a momentary close. This is just closed. Then of course the coil remains energized, and then the coil then closes the main contacts. This is not a motor. This is just a coil that's closing the main contacts that we're not seeing on this particular graphic. It's closing these contacts right here, except it's replacing this with a switch rather than a momentary close. Steve?
And what you just said can't be said enough, Mike, that's not the motor, it's a coil. That's one of the most common areas I see beginning students get so confused about.
You know why they get confused? Because I remember when I first got into controls, I didn't know what was the motor, and I didn't know what was the coil, because they were, sometimes they'll show, and I'm not saying in books, I'm just saying, remember when we were taking tests, with the graphics that were shown, they used an M for a motor.
Yeah.
And they used an M that was supposed to represent the coil that operated the M contacts. So what you got to be careful is, if you take a look at the circuit, and if you look at if you understood enough about controls and you look at the whole circuit, then you'd realize, okay, if you had this drawing right here shown, then it's obvious that that is not the motor when you see T1, T2, T3 going to a motor. You understand? That's your line, that's your terminals. This is obviously not the motor, but when you don't know, like you're saying, and you're just getting started with that, this can be incredibly intimidating. And you got to say, okay, sit back, look at the logic you have here. You can tell that's not the motor, that's the control circuit controlling the M coil that closes the main contacts that go from line 1 to T1, line 2 to T2, line 3 to T3, and that's how it works. So you got to get a little bit more experience. But somebody who has a lot of experience wouldn't have been confused. So they don't say, why are you confused? It's come on, look at the circuit. But we don't have the knowledge sometimes. Let's go to remote control introduction. A 2-wire control circuit can be utilized in different ways by replacing the push button with a maintained contact switch. Well, that's one we just saw. So if you close the switch, right now the switch is open, it's off, coil is de-energized, turn the switch on, close the contacts, you're maintaining that coil, which closed the 3 main contacts, in this case here, so that we can then get power to T1, 2, and 3. A separate control circuit can be used to provide a lower voltage for the control circuit. Let's take a look at this. This is a 480 volt 3-phase contactor. We have 40 volts coming in, and actually, I'll have Mike change these colors. We have black, red, blue, and we just use it in our office as a standard color code. Black, red, blue, white for 12208, and we use brown, orange, yellow, and gray for 277 480. It's really not related to the point here, but let me talk to you guys. What is the practice in the industry for you guys, Steve? What have you seen?
That's what our area where
Brown, orange, yellow for the higher
Pretty-
voltage, black,
pretty
red, blue?
commonly, yeah. You might get into some industrial locations where they might use all black and number them or something, but general commercial wiring, it's going to be brown, orange, yellow.
Eric?
Well, for us, 480 is low voltage, so it's black, red, blue.
Is that really true?
Yes, it is.
Well, I mean, I know it's low voltage is low voltage. I mean, 480 is low voltage for
480 is
Dow
low
Chemical.
voltage, and so, yeah, it's black, red, blue.
Okay, well, okay.
You don't use
Dan?
bell wire.
Our industry standard is the same. We normally use the brown, orange, yellow. We have a lot of older equipment that doesn't have that.
What do they just use all black?
Well, in the old days, it was a lot more common to use like all blacks, like 3 blacks, 3 reds. And if you broke a conduit, it was a lot easier to fix because then you hooked all the blacks together, hook all the reds together, hook all the blues together. Then all you had to do is check rotation. If you use all brown, orange, yellow, you have to get out the ohm meter and ring out each wire.
Yeah,
make
and,
sure
and if
which
you have
motor it
brown,
goes
orange,
to.
yellow, and then you had the wrong phase rotation, then you'd have the wrong color on the wrong phase
Well,
in
you
order to
might
get that
have-
motor to run.
Brown from one motor and orange from the next motor and yellow from the next motor.
Okay.
So
Dennis?
that's the advantage of using all the same color, even though you're not supposed to do that anymore.
Well, you can. There's nothing that says you can't, right? Use all the same color.
Yeah, you can. You just have to mark it at every junction box.
That's true. Yes.
Yeah, and it's become industrial standard that when you're dealing with 12208, you look at, black, red, blue. When you go up to 480, typically it's going to be brown,
All
orange,
right.
yellow.
All right. So let's go on. So we'll go ahead and get this brown, orange, yellow colored on all our 480 volt graphics that we're working from. All right. So, but you know what? If we want, a separate control wiring so I can go ahead and run 120 volts though, and put a single pole switch. Let's say if that's what I was going to do, single pole, single throw switch, and just provide power. So here's the neutral. Here's my coil terminals. All I got to do is get 120 volts to this coil and energize the coil, close 3 main contacts, and motor's running. So you could use 120 volt for controls, which is low voltage. Steve?
Again, something that beginning people may be wondering is, how can we use just any voltage we want to it? We have to change the coil.
Oh,
To match the voltage.
Talk to me about that.
Well, maybe you buy that starter, it has a 480 volt coil in it, that's what you're going to work with unless you've got a different control circuit. Then you can take those screws off the front of that diagram we're looking at and take out the coil and put in a coil that's rated at the voltage that you want to use. So you have to change that out. You have to buy another coil at the supply house if you're not going to use what the starter came
Is that pretty
with.
standard?
Yeah, and you can order them in with any voltage in it that you want.
So if you knew what
order
you
them.
want in advance,
Yeah.
just
But
get
if
the
you
one
don't
with the
know what you
120 volt.
advance, yeah, but if you don't know what you want in advance, you're just going to end up whatever they have on the shelf. So
Gotcha. Gotcha.
Yeah,
Makes sense.
one other thing before, if you look at figure A versus figure B, notice in figure A you're not using the overloads, the overload contact, where in and it tells you that in figure B. So I mean that's what's nice about being able to start to understand the symbols and looking at the figures.
Yeah, and so what we have here, and let's see if we've been looking at this, we've been dealing with contactors,
yes.
not motor starters. These are just contactors. This
Right.
is, and we're going to talk about why and the differences. We've talked about relays, we talked about contactors, starters, but we really haven't put the whole package together. A couple of times we've talked about it, but we'll do it again though. Let's talk about a lighting contactor. A contactor used to control lighting circuits or a lighting panel is called a lighting contactor. All right, let's follow this logic here. I got 6 circuits, line 1, 2, whatever. Let's say 6 circuits. And then I got 6 circuits leaving. So 6 circuits coming in, These, the neutrals are not being shown. And then I got a control relay that if I energize this coil, I will then close all 6 contacts. So if I want to turn on 6 circuits at one time or turn off 6 circuits, a bank where you got a sign and you got parking lot lighting and you want to be able to, it's not, a time clock is good for what, 2 circuits. You get past 2 circuits, well then you can't use the time clock unless you use multiple time clocks. So then get yourself a lighting contactor, get a coil. Let's say here is, we probably should make this 120 volts. We'll make this a black and a white coming in on the line. And then we'll go ahead and run a neutral on the load side, and we'll make this a 120 volt coil. And so if I close the contacts of the time clock, I then will take 120 volts over to the coil. I energize the coil, close the 6 main contacts to the lighting contactor, then the 6 circuits will be energized. And what I like about this one here is a 2-wire circuit, is that in series, if I put a photocell in series with a time clock, so here is power coming in, let's say this is line 1 coming in, and probably the neutral will be just run right through, and then, or I guess 220 is fine, line 1 comes in, and then if the time clock is closed, and if the photocell is closed, then the coil is energized, then the 6 contacts will close, resulting in the circuits being energized. So we have the time clock and the photocell in series with each other. And what I like about this configuration is that, you know, because the way the sun, relative to the rotation of the earth, or the earth's on its axis, some time of the day, the sun, maybe sunset is going to be 5:30. And then during, let's say, the summertime and the summer solstice or whatever close to that period of time, it might not be until 8:30 sunset. Well, if you use a time clock, then you got to keep adjusting the time clock as the sun sets. But if you put a time clock, say, you know what, have the light come on at 5 o'clock. That's it. Well, it doesn't get dark